Good morning, students. Once again, we are discussing the chapter of divisibility and the concepts of various types of divisibilities and its properties. So today's I'm starting with Bizout's identity. So let us see what is Bizout's identity first of all. Bizout's identity, or sometimes known as Bizout's lemma, it says that if D is a common divisor, greatest common divisor of A and B, then it can always be expressed as a linear combination of A and B. So you can say that if D is greatest common divisor of integers A and B, then there exist integers x and y such that D can be expressed as ax plus by. So before moving on to the proof, I like to tell you that this combination ax plus by is not unique. So there are several, or you can say infinitely many combinations of linear combinations of A and B which will result in the greatest common divisor D. So let us prove now Bizout's identity. So let A and B be any integers. Consider the set S of the integers of the type ma plus nb, where m and n are any integers and ma plus nb is greater than or equal to 0, or strictly greater than 0 you can say, or strictly greater than 0, and it is possible. Why it is possible? Because a and b are any integers, m and n are also integers. If you take m to be 1 and n to be 0, the result will be A. If you will take m to be minus 1 and n to be 0, the result will be minus A. If you will take n to be 1 and m to be 0, the result will be B. And similarly, if you take n to be minus 1 and m to be 0, the result will be minus B. And at least one of these is a positive integer. So that means this set will contain positive integers. So this set is non-empty. So this is a non-empty set of positive integers. Therefore, by well-ordering principle, it must have a least element. So therefore, by well-ordering principle or well-ordering theorem, you can say, by well-ordering theorem, there will be a least element. There will be a least element in this set S. Let it be D. Let it be D. Now what is D? D is the least element of this set. So that means D is also a linear combination of A and B, because the set S contains only the linear combinations of A and B, and D is a member of S. So D must also be of the type PA plus QB for some integers, for some P and Q belonging to the set of integers. Definitely it will be like this. Now we will show that this D is nothing but it is the greatest common divisor of A and P. And since it is being written in the form PA plus QB, it will be shown that the greatest common divisor of A and B can be written as a linear combination of A and B. This will be automatically shown if we show that D is greatest common divisor of A and B. So our main focus is now, our main concern is now to show that D is greatest common divisor of A and B. For this we will have to show that D divides A, D divides B, and if there is some other integer D dash which divides A and B both, then D dash must also divide D. This is the main point of focus where we are to go, where we are to move, what we are to prove. So first of all, I'll show that D divides A. And on the same lines, in a similar way, it can be shown that D divides B. So just by showing that D divides A, it will automatically be shown that D also divides B. On the same lines, or you can say in the similar way. Divide A by D. Divide A by D. If you divide one integer by some other integer, some positive integer, then definitely there will be some quotient and there will be some remainder. What you are going to do here, you are dividing D by A by D, so definitely there will be some quotient and there will be some remainder by division algorithm. So this A can be written as DQ plus R. So then this A can be written as DQ plus R, where what is R? R is the remainder. Remainder is always greater than or equal to 0. So your R is greater than or equal to 0, but is strictly less than the divisor. So R is strictly less than D. So this is the thing where we are now. So A can be expressed as DQ plus R, where R is strictly less than D but is greater than or equal to 0. Now look at, if we prove that this R is equal to 0, then automatically we are through, because R is equal to 0 means this is 0. So A will be DQ and that means D divides A. So now our main focus is to show that R is 0. Note that this R from here can be written as A minus DQ. You can write it like A minus, what is your D? Your D is PA plus QB. Or you can say 1 minus P times A plus minus Q times B. That means R is a linear combination of A and B. And R is greater than 0 as well. It's just strictly greater than or equal to 0. Now, R is a linear combination of A and B, and all positive linear combinations of A and B are the members of S. So that means this R must belong to S. And your R is less than D. But by our choice, D is the smallest member of the set S. How is it possible? D is the smallest member of the set S, and R, which is less than D, belongs to S. So this is a contradiction. And why this contradiction is that here? Because we have taken R not to be equal to 0. That means R must be equal to 0. So R is equal to 0 means from here you can have your A is equal to DQ. And when A is equal to DQ, this means your D divides A. On the same lines, in the same fashion, in the similar way, we can show that D also divides B. So D divides A, D divides B, it's okay. Now, D is a common divisor of A and B. But we have to show that the D is greatest common divisor. For that, we have to show that if D dash is some other common divisor of A and B, then D dash divides D also. So let D dash be some other divisor, common divisor of A and B. So D dash divides A and D dash divides B. If D dash divides A, then D dash divides every multiple of A. So why not MA? So D dash divides MA, PA, QA, RA. So why not D dash divide PA? It will divide PA. Similarly, D dash divides B. So D dash divides every multiple of B. So D dash must divide QB. And if D dash divides these two numbers, that means D dash must also divide their sum, PA plus QB. But what is your PA plus QB? Your PA plus QB is your D. So D dash divides D. So what we have shown? We have shown that D is a common divisor of A and B. And not only the common divisor, it is the greatest common divisor, because if some other divisor D dash divides both A and B, then D dash also divides D, which shows that D is the greatest common divisor of A and B. So that means your D is the greatest common divisor of A, B, and we have proved. Because what we wanted to show that the greatest common divisor of A and B can be written as a linear combination of A and B, and D is the greatest common divisor of A and B, and D, by our choice, is a linear combination of A and B. And as I have told you earlier, that this linear combination is not unique. There are many possibilities of P and Q which will make this linear combination equal to the greatest common divisor. So this is to be kept in mind, that the expression D is equal to PA plus QB, that means the expression in which we write the greatest common divisor of A and B is a linear combination of A and B is not unique. So with this theorem, I'll move on to the next one. The next one is having several parts. So you can just see this theorem before moving on to the proof. Theorem is that if A and B are any two integers, then greatest common divisor of AB is same as greatest common divisor of BA, which is very much obvious, is also equal to the greatest common divisor of plus minus A and plus minus B, is also equal to the greatest common divisor of A and B minus A, is also same as the greatest common divisor of A and B plus A, is also same as the greatest common divisor of A minus B and B, is also same as the greatest common divisor of A plus B and B, is also same as the greatest common divisor of A minus B, A plus B, etc., etc., etc. So many parts are there. So I'll like to prove one part. I'll prove just one part, and the proof of the rest parts is almost similar. So what I'll prove, I'll show, suppose AB and B minus A. Let me take this part. So what I'm going to prove now, I'm going to prove that if A and B are any two integers, then greatest common divisor of A and B is the same as greatest common divisor of A and B minus A. If I show that every divisor of greatest common divisor of AB and every divisor, or you can say every common divisor of A and B is a common divisor of A and B minus A, and every common divisor of A and B minus A is a common divisor of AB, then in fact what we have shown, that the common divisors of A and B and the common divisors of A and B minus A are same. And if their common divisors are same, automatically their greatest common divisor will also be same. So that trick I will use here. I'll show that if D is a common divisor of A and B, then D is a common divisor of A and B minus A also. And if D is a common divisor of A and B minus A, then D is a common divisor of A and B also. This I'll show, which will mean the common divisors of A and B and the common divisor of A and B minus A are all same. And as I told you, if the common divisors are same, exactly same, then the greatest common divisor must also match. So let D be a common divisor of A and B. So that means D divides A and D divides B. Now, if D divides A and D divides B, then it is clear I can write D divides A, D divides B, and I can also write if D divides A, then D also divides minus A. Because if D is a divisor of A, then D is also a divisor of its negative. Now, this implies D divides A, and from here, if D is a divisor of B, D is a divisor of minus A, then D is a divisor of sum of these two. That means D is a divisor of B minus A. So this means D is a common divisor of A and B minus A. That means every common divisor of A and B is a common divisor of A and B minus A. And now we'll prove it on the other way, that is every common divisor of A and B minus A is a common divisor of A and B. So let now D be a common divisor of A and B minus A. This means D divides A and D divides B minus A. And it means D divides A, and if D is a divisor of these two, then D must also be a divisor of sum of these two numbers. So that means D divides A plus B minus A. And what is A plus B minus A? It is nothing but B, because A will be cancelled here. So that means D is a divisor of A and D is a divisor of B. That means D is the common divisor of A and B. So this means D is a common divisor of A and B. And that means every common divisor of A and B minus A is a common divisor of A and B. And in this way, we have proved that common divisors of A and B and common divisors of A and B minus A are exactly same. And if the common divisors are exactly same, then greatest common divisor must also be the same. So this is the proof of one of the parts. The rest of the parts you can prove in the same way, in the same fashion, in the same line, in a similar way. And now I'm moving on to the next part, the next question, the next property, the next theorem. And it is, if greatest common divisor of A and B is D, then greatest common divisor of A upon D and B upon D is 1. And how we will prove it? We will prove that A upon D and B upon D have no common divisor greater than 1. And we will prove it using the way of contradiction. On the other hand, we will suppose that there is some integer which is greater than 1 and which divides both A upon D and B upon D. Let E greater than 1 be a common divisor of A upon D and B upon D. This means E divides A by D and E divides B by D. And if E divides A by D, definitely there will be some integer k or k1 such that A upon D can be written as k1e and B upon D can be written as k2e for some k1, k2 belonging to the set of integers. And from here you can write A is equal to k1 ed and B is equal to k2 ed. And this means ed divides A and ed divides B. And this means ed is a common divisor of A and B. So this means ed is a common divisor. This means ed is a common divisor of A and B. Now here your E is greater than 1. E is greater than 1 and D is positive because D is the greatest common divisor of A and B. So D must be positive. So multiplying both sides of this inequality by D, what you are going to get that ED is greater than D. ED is greater than D and ED is a common divisor of A and B is a contradiction because D is the greatest common divisor. If D is the greatest common divisor of A and B, then a number ED which is greater than D cannot be a common divisor of A and B because D is the greatest. If D is greatest, then a number greater than D cannot be the common divisor of A and B. And here we are getting that ED which is greater than D is a common divisor of A and B. So we are arriving at a contradiction. And this is a contradiction. Why? Because our supposition was wrong. And what we have supposed that there is an integer greater than 1 which is the common divisor of A by D and B by D. That means no integer greater than 1 can be a common divisor of A by D and B by D. And if no integer greater than 1 can be a common divisor of these two quantities, then clearly their greatest common divisor will be equal to 1. So in this fashion, in this way we have proved that if the greatest common divisor of A and B is D, then the greatest common divisor of A by D and B by D is always 1. And now another theorem, prove that greatest common divisor of A and B is same as greatest common divisor of A plus CB and B for every C belonging to the set of integers. And the proof I'm not going to do. I'm leaving this theorem for you people, for you students. Why? Because the proof is almost same as the proof what we have proved in greatest divisor of A, B and greatest divisor of A and B minus A are same. So the way in which you have proved this, you can prove this as well. So it is an exercise for you to try, and I hope you will be able to prove this part. With this, I'm going to leave you here. I'm stopping this video here. In the next video, we will have more and more theorems, lemmas, properties about divisibility. Thank you all.